Alright, so I'm going to go ahead and do a little chemistry lesson here, and maybe it's something you haven't seen before, but something that I either figured out or maybe I heard at some point in some class where I was trying to stay awake and ended up rediscovering in recent years. If we look at this chemical equation that we've got over here, we've got C5H9O plus oxygen goes to CO2 and water. And in traditional high school chemistry class, they just have you try to, well, first off, we see that this is an unbalanced equation. And in a typical high school class, they would tell you to just kind of keep guessing numbers and adding up atoms to see if you can get it to balance. And for some equations, that works out great. But then for others, it's just a really tedious process, and there's got to be a better way. So for those of you who aren't afraid of algebra, let's look at something that maybe you did in Algebra 2 that we can use with this chemical equation to help us balance it more quickly. So, looking at this equation, if I were to assign a coefficient to each of these items here, so we'll call this one A, and let me see if I can find a better brush than that. Call this, whoa. Sorry folks, let me retry that. Call this one B. C. And D. Those are really sloppy, but you get the idea. Now, in order to deal with this, we know that for every carbon atom on one side of the equation, we have to have a carbon atom on the other side of the equation. And same with hydrogen and oxygen. So what we can actually do is set up a system of equations that deals with each of these. We can come up with an equation for each of these elements. So if we look at carbon, we can see that on the left side of the equation, our reactants, we have 5 carbon atoms times the number, times the coefficient in front of C5H9O. So in other words, that's 5A. But on the left side of the equation, on the right side of the equation, our products, we can see that we have a carbon for every CO2 atom, or CO2 molecule. And so that's how the number of those is C times 1. So just C. And we do the same thing for the other atoms. So if we do hydrogen, we can see that we've got 9A on the left side. And in this case, we have 2 hydrogens for every water molecule, and then the number of water molecules is D, so we basically have 2D. And we do the same thing with oxygen. In this case, we have A plus 2B. You can see where that comes from. And on the right side, we have 2C plus D. Okay. So what we have here is 3 equations and 4 unknowns. So what we're actually going to end up with is a system of equations that has an infinite number of solutions, and we'll deal with that later on. But really what we want to do is show the relationship between all of these coefficients. So what I'm going to do, I'm going to solve all of these in terms of A. So in the end, I want everything to equal some number of A. So in the case of our carbon, we're already set. We know that C equals 5A. And so that works out. So then, what are the ones that we want to do? We've got this hydrogen here. We can say that we solved that equation, 9A equals 2D. We solved it for D. We'd divide both sides by 2, and we'd end up with 9 halves times A equals D. Okay. So at this point, I've converted this one. I've converted this one to A. So now I just got to get rid of this B. So also look at this and say that bottom equation there for the oxygen, we've got A plus 2B equals 2C, which we know is just 5A, plus D, which we know is just 9/2 A. So if we look at this, we can start combining like terms. I'll leave the A plus 2B on this side for now. We have 10A plus 9/2 A. And 9/2 A is really just, or rather, to convert those, we'll go ahead and make this 20/2 A plus 9/2 A. And all I really did was get a common denominator between them. So we end up with A plus 2B equals 29/2 A. We subtract A from both sides, or another way to look at it is 2 over 2A. We have 2B equals 29/2 A minus 2/2 A, which is just 27/2 A. And then if we divide both sides by 2 to get B by itself, we end up with 27/4 A. So now what we have is we have all of these in terms of A. So we could rewrite this entire equation as A MA C5H9O plus 27/4 times A O2 and that all goes to 5A CO2 plus, where D is 9/2 A times A 2O. So now at this point, there's a solved system, and any value of A will mathematically make this work out. But in chemistry, we like to have the smallest coefficients we can, and we like to not have fractions for coefficients. So looking at this, I have two fractions to deal with. I've got this one here and this one here. So I'm going to choose A to make those fractions go away. So I'm going to choose A equal 4. So if we do A equals 4. Now we can say 4C5H9O plus 27/4 times 4 O2 goes in, it becomes 5 times 4 CO2 plus 9/2 times 4 H2O. And if we simplify that, that's just going to be 4C5H9O plus 27O2 goes to 20 CO2 plus 18 H2O. And so, if you don't believe that that works, we can add up both sides. So, on the left side of the equation, we have 4 times 5 is 20 carbons. And on the other side, we've got 4 times 5 equals 20. For our hydrogens, we have 9 times 4, which is 36. And on the left side, or I mean on the right side, we've got 18 times 2, which is also 36. And then for our oxygens, we have 4 plus 27 times 2, which equals 58, I believe. And then on the other side, we have 20 times 2 plus 18, which also equals 58. And so this will work with a lot of equations. Instead of trying to guess, I mean, you can imagine how long it would take us to guess numbers and end up with this equation right here. So, I mean, the 4 and the 27, that would have taken a while. So this is just a faster way to do it, in my opinion. So hope you enjoy, and hope this is helpful for you.